So good morning, everyone. Uh, Welcome you all on this first session for the QIP course on 4D printing.
Good morning, sir.
Yeah. For this session, we have specifically requested Professor P.M. Pandey from IIT Delhi. We are fortunate enough that Sir is with us. Some of you may be knowing Professor Pandey, and those who are not knowing, we will just understand after his lecture that he is the authority in the area of 3D printing. In our country, I suppose he is one of the most decorated professor who have worked in this area of 3D printing. If I say just few about Professor Pandey, he has completed his bachelor's from HBTI Kanpur, scoring a first position in university, then masters from IIT Kanpur, PhD from IIT Kanpur. He has served for a couple of years at HBTI, and since 2004, Professor Pandey is working at IIT Delhi. Sir has supervised more than 32 PhDs in the area of manufacturing and major focus on the 3D printing. Professor Pandey is holding 21 Indian patents, more than 185 SCI journals, number of national international conferences, having a H index of 38 with more than 6,000 citations. He has been awarded the Best Paper Award by RP Journal for the working in the area of fabrication of three-dimensional open porous regular structures or PA 2200 for enhanced strength of scaffold using SLS. This was published in 2017. Not only Professor Pandey has elaborated work in the area of 3D printing, even his bachelor's and master's students, they have also received number of awards in the area of 3D printing. Sir is recipient of Outstanding Young Faculty Award from IIT Kanpur. Then, of course, JM Mahajan Outstanding Teacher Award from IIT Delhi. Then, of course, he has won GYTI Gandhian Young Technology Innovation Award continuously in 2013, 15, 17, 18, and 20. We are really fortunate to have an interaction with Sir. I request Professor Pandey to please start his proceeding. Welcome, Sir, from Little Chandigarh side.
Thank you, Professor Rupinder Singh ji. Uh, it's my privilege that this opportunity has been given to me to talk about my research area and contributions. I'm thankful for your very generous introduction. Okay, so I have to take my presentation in a different manner because the topic which was mentioned in the brochure is about bone drilling. So exactly this bone drilling is not related to additive manufacturing, but because it has been written, so I'll show you some slides about that also in between. But before really proceeding further, I would like to talk about one of the themes which we are having in this for this presentation. So that is my idea. So let me share my screen and talk about the lecture. So I'm audible, I believe.
Yes, sir, loud and clear, sir.
Okay. So how many participants are there presently? Let me just see. 59, I think, correct? There are 59 people in this meeting. 58 or 59. So can you just let me know that how many of you have already heard me talking online? Because these days, I think every week I used to have one lecture in one of the FDPs. So I believe some of you might have already heard my lecture. Yes. Jaspreet Singh. Yes. Anybody else? Can you just write on the chat box? Yeah. So 5. Okay. Okay. Only 5? Okay, thank you. So 6, few more. Yeah. Okay, so some of the slides are definitely will be repeated. So I have already shared my screen or not? No, I have not yet shared. So let me share my screen. Okay, so in between I will talk about the bone drilling also, but exactly I will talk about the how really the smart manufacturing and additive manufacturing, which is, I'll say, uh, matured technology now. It's not fully matured, but definitely a lot of uh, things have been done and it is usable in industries nowadays. 4D printing is something which is at its infancy. It's the concept has just emerged, and we have started our work. Some of the work has also been done at other places. Dr. Rupinder ji has also done some work. I am also doing some work, though I have not published anything till now in the area of 4D printing, but I'll just tell you what 4D printing is. But actually, it is an extension of 3D printing only. So let me talk about the smart manufacturing, and then I'll connect it to additive manufacturing. I'll talk about in between bone drilling also, and I will talk about the latest AM processes, though I was observing that you might have already heard, but maybe something new I can tell you, and few projects which we have done at IIT Delhi recently, and in those one of them will be the bone drilling, which I'll touch upon. Because I'm not focusing fully on that, because it does not involve much 3D printing or 4D printing or maybe the smart manufacturing, because it is a different kind of work. Anyway, so let me talk about smart manufacturing first. So today, this is a very catchy and key word, Industry 4.0 or smart manufacturing. So we have to understand what it is and how really this particular concept of manufacturing, I must say, or a scheme of manufacturing or a philosophy of manufacturing, how it is useful for us and for a society, for individual, for nation. That's how we have to understand. So in order to understand what really it is, we have to see the background. So like this industry 4.0 is actually the fourth industrial revolution. And before industry 4.0 or fourth industrial revolution, obviously we had three more industrial revolutions. So first industrial revolution was about mechanization. Mechanization means when the primitive machines which were there at that time, because this particular industrial revolution took place at the end of 18th century, correct? So at that time the primitive machines, because if you have a machine, I'll say that a simple lever is also a machine. Now if you have to, until you energize a machine, you cannot take work from a machine. So from where you will get that energy. So at that time, in order to drive or in order to take work from those primitive machines, it was the human muscular energy or the cattles. They were employed to drive those machines. Then, people kept on doing innovations. People have developed some very primitive type of water turbines, and they derive the energy from the flowing river. So all those kinds of things people were trying. The materials were also developed at that time, and it was the time when the iron ore was processed in a very nice manner, and people started developing steels. So the steel development that brought some sort of, I'll say, very nice and strong, tough material was made available to the society. So all these things together actually brought the first industrial revolution, but the key word here is the mechanization, and this mechanization has actually taken place because the James Watt developed the steam engine. So the steam engine development brought first industrial revolution because all these primitive machines which were developed and were improved because of the development of iron, steel, mining and metallurgy technologies. They were, energized by the steam power, and the human muscular energy or the cattle based systems, they were replaced by the steam or water power. So that brought the first industrial revolution. Now the after around 100 years or so, more than 100 years after first revolution, the concept of production line that came into the picture, which actually facilitated the mass production. So technological electrification, the electrification also came into the picture at that time, and there were a number of engines or turbines they were developed. Telegraph was developed, gas and water supply was developed, but the key word here is the mass production through the continuous production line. So when this concept of continuous production line for replicating thousands of components or products in a very short span of time that was developed, it was the time when called it second industrial revolution. Now, after this, around 1970s or so, it was the time when microprocessor was developed. Now, development of microprocessor is actually the initiation of electronics, or we can say digital age, or the digital concept of digitization. So from the development of microprocessors, so many other things, related things were developed, like computers. Internet started little later, but it was also related to that. Then for manufacturing, it was the initiation or the beginning of numerical control systems, which were digitally controlled, and at the same time, the concept of robotics, like that was also came into the picture. All these things actually brought some sort of automation. So programming logic controllers, they were developed. So they brought the automation in the field of manufacturing, and bringing the automation and controlling the machines or machine tools with the aid of numerical control or microprocessors is something which is termed as industry 3 or third industrial revolution. So this third industrial revolution is basically the substitution of human mental effort. So in first industrial revolution, human muscular energy that was replaced by the steam or water power, and in the third industrial revolution, it was the mental effort that was substituted by the microprocessor, or we can say numerical control, by bringing numerical control to the manufacturing. Now today we are talking about smart manufacturing, that is industry 4.0, and this industry 4.0 is basically because of the convergence of information technology wireless communication technology, and so many other related tools which have been described in this slide, like big data analytics, Internet of Things, Internet of Services, cloud, smart factory, machine learning, AI, and of course, these whole things constitute a cyber physical system. So, if I talk about a manufacturing technology or a manufacturing system which is being enabled or being assisted, or we can say the the information technology as well as the wireless communication technology also taken along with the manufacturing in order to improve the manufacturing scenario, then it is called as Industry 4.0 or smart manufacturing. So this is the most, I'll say, advanced concept which we talk about today. So in this slide, I have tried to show you, though the slides are not my own slides, the source I have already mentioned. So here, the first industrial revolution took place around the end of the 18th century, and beginning of the 20th century, we talked about continuous manufacturing. Then 1970s or so, we talk about use of electronics, and maybe the numerical control, robotics to the manufacturing. And today we talk about cyber physical system based manufacturing, that is the industrial revolution. So here I have shown level of complexity. The level of complexity in manufacturing that that is keep on increasing over the different industrial revolutions. Okay, so the backbone of today's concept of smart manufacturing is actually cyber physical system. So what is a cyber physical system? Cyber physical system is something which can be schematically demonstrated as I have shown in the slide. So on the core, on the heart of the cyber physical system, we have huge digital information. Like over the years, so many engineers, so many researchers, they have developed a lot of data, and if that data is made available in the digital form, like you can visualize the situation, like there are machining handbooks, there are handbooks related to additive manufacturing, there are handbooks related to grinding, correct? There are handbooks related to casting technology. So this is also the information, but this information is not a digital information. Is it okay? So now this information has to be made available, or it has to be, it has to be digital information, and it should be present with the cloud. And from this digital information, if I want to produce a component, for example, I want to produce one component, and so I need some information, some digital information, some information from this huge information which is useful to me. So how to derive that information, how to get that information, correct? So that is being done through computation, because if there's a lot of information and it is available in digital form, you need to have some tools to find out appropriate and optimum information for your use. So you need to have big data analytics, you need to have optimization, you need to have artificial intelligence to evaluate the various options available with it. And then you will get actually the information which is of your use. So this actually requires a lot of computation. Now this data which you have actually taken out of computation is to be communicated to the various locations where it is to be used or executed. And then we are going to have physical entities, and these physical entities may be the machine tools, they may be the robots, they may be some other manufacturing aid which is to be controlled at that particular physical location. So you need a lot of communication, and then appropriately, you need control, correct? And this communication is not one-way communication, rather it is a very networked communication, which may be among, your digital hub. It may be among various machine tools or the various physical entities which are under, uh, uh, operation in order to, in order to enable or in order to continue that manufacturing operation. So a cyber physical system is a system of collaborating computational elements controlling physical entities. So CPS are physical and engineered systems whose operations are monitored, coordinated, controlled, and integrated by a computing and communicating core. They allow us to add capabilities to physical systems by merging computing and communication with physical processes. This is how we can have a feel of actually cyber physical system. Now, this schematic diagram just gives you a feel, but actually it in order to, actually achieve it, there are several technologies which are not only related to mechanical engineering, but they are also related to electronics, information technology, computer science, mathematics, and many other, branch of engineering together. So I'll show you those things in my forthcoming slides. So anyway, so today, what is the concept of today's factory? Like, if you go to very successful manufacturing plants in our country or maybe in abroad also, you will find that this is the kind of manufacturing factory we are having. This one example has been shown in this particular slide. That is a continuous assembly line for automobile production. So a car is being produced, and this kind of assembly line you might have observed when you visit any automobile company, maybe anywhere in our country. This very advanced, like Suzuki, Maruti, maybe the Honda, Hero Honda. All these companies, they have this kind of systems. Correct. Now you might have also seen that there are if there are more models of a particular, like if you vehicle, like if you go to the company A, it has car A1, A2, A3, A4. Number of models are there, the way you have models, number of models for say Maruti car. So you will find that there are different assembly lines which are dedicated to different models. You will hardly get a situation that two or three kinds of models of a car, they can be assembled or they can be produced on a particular assembly line. So what do you see is that it is a rigidly sequenced car manufacturing on a production line. So this though it is a very nice way of manufacturing which has actually emerged at the Industrial Revolution 2 time, which is also ongoing today in a very enhanced, along with very enhanced capabilities, still it has a limitation that it is rigidly sequenced. It is not flexible to the various, variants of that car. So this is something which is the today's production system is. But what we are talking in smart manufacturing, that this entire thing will be driven through a data which is being communicated to various workstations which may be present, at different premises in a company or maybe at different locations physically, and they are all being communicated the data to which they will operate, through which they will operate. And these workstations also have capability. They are enabled with Industry 4.0 modules that they can communicate with each other or one another. And that's how you are able to achieve a fully decoupled, fully flexible, and highly integrated manufacturing system, which is today we are calling as smart manufacturing. So if you have this kind of manufacturing system, you will be able to actually handle different kinds of products. Means, or you can say, if I want to be more precise, I can say the different kind of models of a particular car, they can be done on this kind of integrated manufacturing system. Now, I had an opportunity to visit Germany 2 years ago, and I could visit this automobile companies like Audi. It's not Audi. What is that? I actually forgot all these names. What are the German cars are? Mercedes Benz, and then one more company is there. So I had a visit. Now there I could see that definitely they are able to actually modify this concept of today's factory. Means they are little ahead, but definitely they have not reached up to this kind of concept. Correct? So what they are able to do, that if there means in one assembly line, they are able to assemble or produce more than one kind of car, provided there is a lot of similarity. So definitely they have introduced some degree of flexibility in their assembly lines. Means they have actually moved forward towards bringing more flexibility in their production line. They are not very rigid in their case. But what we are talking today, that it has to be completely flexible, fully flexible. It is fully decoupled also, but definitely this system is not a decoupled system. They are rigidly sequenced. Correct? So this is something what we are trying to implement, and definitely though I did not have any opportunity, but we have few companies which are able to implement it within their premises. Okay. So there are 6 typical design principles which you have to think about. One is called interoperability. Now this interoperability means the ability of cyber physical systems. They are like workpiece carriers, assembly stations, and products. Humans and smart factories to connect and communicate with each other via Internet of Things and Internet of Services. So this kind of property, or this kind of capability, in if you introduce in your manufacturing system, this is called interoperability. Then virtualization means this concept, you know that there's a virtual simulation we talk about. Correct? A virtual reality we talk about. So virtualization means a virtual copy of the smart factory, which is created by linking sensor data with virtual plant models and simulation models. So simulation is one thing. Virtualization, by creating a model which is based on the sensor data. Now here there are two things. Suppose I try to develop a assembly, and I can simulate the assembly using finite element software, multi-body dynamics. So that is a simulation model. Second thing may be that I can have that particular assembly perform the number of experiments, take the data, secure that data, develop a AI model, and use that AI model for virtualization. So that is a different kind of virtualization. Correct? Now then decentralization. Decentralization means the ability of cyber physical system within smart factories to make decisions on their own. So there's a vertical and horizontal decentralization. Then real-time capability. This is something related to adaptive system, adaptive controls. The capability to collect and analyze data and provide the insights immediately. Means your system is working, your manufacturing facility is working. Correct? It is an integrated, fully flexible, and it is a decoupled system. And Definitely, if any manufacturing system is there, any product is there, it cannot keep on working forever. There will be some problem somewhere. There are likely to be some defect somewhere, correct? So once you are having those defects somewhere, the system, your manufacturing system, should be collecting the data, because you are having smart components, you are having smart assemblies, correct? So these smart assemblies, your smart components, they can be produced by additive manufacturing. I will talk about those things in my second part of the presentation when I'll start talking about uh, additive manufacturing or 3D printing. So you can collect those systems will let you know through the data which is being collected when the system is working, and the corrective action will be taken immediately in between. So the capability to collect and analyze data and provide the insights immediately. Then service orientation, of course, offering of services, correct, via Internet of Services. And modularity. Modularity is something that flexible adaptation of smart factories for changing requirements of individual modules. Like one example can be given, that you have a car and the car has one kind of braking system. You want to change the braking module and you want to convert it to some sort of advanced disc brake kind of system. So this is your assembly line or your manufacturing system should be able to flexibly adapt, and the changes can be done if there is a dynamic requirement by a customer. So that's that kind of scenario which we are talking about is related to smart manufacturing. So I was talking that you can achieve, like one can achieve this smart manufacturing because you need to take several technologies together. It is not being done only by mechanical engineer, it cannot be done only by electronics engineer, it cannot be done only by information technologies, because there are various technologies which are likely to go together if you really want to implement industry 4.0. And these technologies are like, you need to have big data analytics, you need to have augmented reality, you need to have autonomous robotics, simulation, decentralization, that is horizontal and vertical system integration, industrial IoT, Internet of Things. And because most of the things you are doing, they are soft in nature, you are actually doing with the digital data and playing with the data, you need to have security for that data. But definitely the cyber security becomes important. And of course, at the end of the day, when you are able to decide everything and you want to convert the things, you want to convert your data to 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 a hard pick, like a product, you need something to produce it, something which can fabricate it. So the technology which has been recommended is the additive manufacturing, correct? So though sometimes I'm not very convinced with this, because if the kind of but it may be true also, because in the coming time, or you can say today, the market has become very much customer driven. And once the market is customer driven, though you may be talking about a car, but the car may be a customized car. And if the situation is like that, you need to have a manufacturing, like in those cases, you will not like to replicate, keep on replicating as we are doing for mass production. So once the customized manufacturing is there, it is the additive manufacturing which is the best suited technology for fabricating or manufacturing the things. So this is how they are having their own roles. Okay, so this is what something I was trying to talk about, that it will become a completely digital enterprise, correct? And in this digital enterprise, you are going to talk about product design, production planning, production engineering, and production. So this production when you're doing, and once it becomes a customized production, then from here only you are getting the hard components. Still, from here to here, you are actually having everything as soft. And from here, there's a role of additive manufacturing that is coming in our way. Now, what are the skill sets which are required for Industry 4.0 or smart manufacturing? So, what we talk about today is like today, all our engineers, they are being developed with number of skills, and those skills involve complex problem solving ability. Students do a lot of coachings, they do a lot of JE preparation or engineering preparation, and they solve very difficult problems. They do a lot of mathematical jugglery, they do very difficult physics problem, correct? So why they're doing all those things? Because they have to develop a complex problem solving ability. Coordinating with others, this is again very important. So coordinating with others is definitely very important, but only for the good means. But what is happening in our society nowadays? I don't want to comment that aspect, but people coordinate, they make teams or gangs, and there's a lot of professional problems. So it should not be for that. The people management, critical thinking. You have to critically analyze and break your project or your problem into small sub problems and solve them. The negotiation, quality control is definitely another aspect of engineering, because if you're producing something and you are selling it to the market, you're sending it to the market, it is going to the customer, you have to maintain the quality, and the quality has to be accordingly maintained. You have to see the cost of the component, you have to see the life of the component, and you have to see what you really want from the product, for how long. Service orientation has to be there, definitely. Customers want service, judgment and decision making capability, active listening, and creativity. These are the skill sets which are required. Now, when you are switching over to the industry 4.0 kind of environment, correct, then obviously number of these skill sets are required, but you need few more things, and these few more things are: one important point is emotional intelligence, and the second important point is the cognitive flexibility. Now, why emotional intelligence is required? Because once you are working in an environment of industry 4.0 smart manufacturing, it is almost manless environment. You hardly have people, mankind, who's actually doing the things. Most of the things are highly automated, they are networked, they are controlled itself, they're taking its own decision. So in those situations, there has to be an emotional intelligence with the human being, and there has to be cognitive flexibility, because you are actually working in such kind of very highly networked environment. So there has to be ability in the human being for working for the different zones, from switching over from one kind of ability to another kind of ability. So definitely this is the kind of thing we are talking about. Now, if we implement such manufacturing system or philosophy, it is going to impact everyone, including individual, society. It is going to impact business, therefore economy of any country, and therefore the economy of the globe, over the globe. So that's how this particular concept is a concept which involves almost all kinds of technologies, modern technologies together, in order to bring revolution in the manufacturing. Correct? And additive manufacturing is something which has been recommended as a tool for smart manufacturing environment. So now in the next part of my presentation, I'm going to focus on additive manufacturing, and because you have already gone through a number of things about 3D printing. Additive manufacturing means when we talk about 3D printing. So what I should do, I will talk about certain, important conceptual points, and then I'll take over to the very advanced systems. And okay, so yeah, are there questions from this part of my presentation? Yeah. So if there are questions from this part of my presentation, I can take few questions and then I can proceed further to the next part of my presentation. So are there any questions? Yeah, so something has come. Are we going to have industry 5 also? Yeah, it's a very difficult question. I think if you're talking about industry 5, what first you have to implement industry 4 fully. I believe that it will not be very uh, early. Like you have to wait. I cannot say no, I cannot say yes, but definitely if it is likely to happen, it will take, I think, long time. It's not going to happen very soon that you get another this thing, because if you really see 3D printing, it has started around 1994. It was the first patent stereolithography that was filed. So it is around 25 years only, and we have still not implemented it fully. It's hardly nowadays it is picking up. I can see that because of the you know uh, initiative which has been taken by AICT in our country. For the last 1 year, I'm observing that there are a lot of uh, workshops or maybe some sort of FDPs or faculty development programs for students as well as faculty members. They are going on and people are getting trained in the area of 3D printing. It is still our industry that has not adopted it with open heart. That is one thing. And today, if we talk about Industry 4.0, that is something which is very, very new today, correct? And hardly we have any company in our nation which has actually moved ahead to adopt it. Only few projects are going on which have been funded by Department of Heavy Industry, and people are trying to develop few things, maybe satisfactory to only some extent. So we have to actually go a very long way. Therefore, at least now I cannot say that in time to come, maybe for another 20 to 25 years, you don't have any scope for any new concept in the manufacturing. This is what I feel right now. Okay, there are sir, feasibility in adapting Industry 4 with production facilities. So I believe I am talking about production facilities only. It is a production scheme. So you have to, of course, implement so many things for doing it. And of course, you have to do the analysis whether really this is needed for your place or not. It's not that every small place will start, adopting Industry 4.0. That it is not a technology, it is not a CNC machine that you purchase and keep in your premises and start working on it. It is not like that. It is a concept, it is a philosophy, correct? That if you have a, suppose you are producing some components, and those components, the demand is very flexible. You get number of components of which are similar in nature. In those cases, you may think of doing it, but it is not, I'll say, recommended when you are having a some sort of SME kind of thing where you are only dealing with one kind of product and having few people and doing their job and producing the things. In those scenario, I do not think that it is something which is recommended. But of course, some of its part, like if some of the SMEs, they start working in a group and they take advantage of these kinds of wireless communication, and maybe they want to utilize the different facilities which are present with the different SMEs together to bring out a product which is a joint project. That may be a situation when we talk about it. Okay, sir, is robot and cobot will come under Industry 4.0? Yes, robot and cobot. Cobot is collaborative robotics when human beings as well as the robots, they work together, and of course there are certain issues there. So it is definitely, I have already shown you that autonomous robots as well as the collaborative robots, they are the part of Industry 4.0. Yeah, any other question? Okay, so if there's no question, I am moving forward with my second part of the lecture, that is uh, so I'll just brief. I believe that most of you may be knowing by now the history of additive manufacturing or 3D printing, that how it has evolved and where really it is important. So the concept of 3D printing, it emerged in the beginning as a rapid prototyping. So this rapid prototyping is nothing but a design. It is used for design evaluation. So once you have developed an optimum design for any particular design need which has been identified by the engineers, converted into the technical specifications, you have conceptualized the design, done the modeling, simulation, analysis, optimized the design, so then you go for prototype. And you have to make this prototype very easily, in a very fast manner, so that this bottleneck, this particular design evaluation step is a bottleneck that is being dealt, or that is being done very fast. This is what we want to do. Then we have to do design communication, that is the making final drawings. Then we do for production engineering, we try to do production, quality control, packaging, shipping. Then the product comes to the market and you again get the feedback from the customers. So that's how this process of design, this becomes a continuous process, and this is a bottleneck. So in the beginning, this particular technology, which is quite, I'll say it is very at quite advanced level now, known as rapid manufacturing or maybe additive manufacturing today, was just a prototyping tool in the beginning. And people did, earlier the prototyping was with the craftsmans, later it was a virtual prototyping or soft prototyping, and at the latest trend has been the layer by layer material deposition method, which is said to be as RP. And it was started, people thinking about it, and because of the CAD, CAM, automation technologies together, they have taken it to the shape. So the concept is very simple. We can remove the material layer by layer, and we produce the components. We can join the two blocks. We can reform the material, known as forming. But here it is a bottom-up approach. And bottom-up approach means there's nothing in the beginning, and we are depositing the material on a platform. In the beginning, there's nothing, and we are keep on adding the material from bottom to the top, which is known as rapid prototyping. So you may already knowing about this, that you start doing with the CAD modeling. So we make a CAD model, whatever I want to produce, I'll do CAD, then I'll do tessellation. Tessellation is the piecewise, there are different surfaces in a valid solid. So those surfaces are approximated by small triangles, which is called a tessellated model. And this tessellated model is being sliced. Slicing is the intersection. There's an intersection of horizontal planes from bottom to the top. So there are different algorithms for this. And once you have this sliced data, this data is fed into the RP system, correct? And you have different technologies. So I believe you have gone through various technologies like FDM, maybe stereolithography, which are liquid based, solid based. Sometimes we use laser also, sometimes we use UV lamp. So depending upon the technology for deposition, we have this 3D printer, either in the process software or maybe outside, it does some other calculations. Like if you go to like this openware softwares, freeware softwares, for FDM, you have number of, say, K slicer, this slicer, that slicer. So many softwares are there. So you do selection of some process parameters. You do selection of infill patterns, that how to fill a layer. All those things you do, and then basically you feed the data to the system. The system deposits the material layer by layer, and you get the component. And this component is post-processed, it is finished, or the supports are being removed, and you get the prototype. And if there are drawbacks in the prototype, you redo your CAD model, otherwise it is a final prototype. So this is how the thing works. So if I have this is a virtual model of a component, correct? And this is the concept of tessellation, that a free-form surface, or maybe any surface which is present on a solid model that is being approximated like small triangles. Then you do slicing. Once you do the slicing, you basically get nested polygons, correct? So these nested polygons are being written in standard formats like SLC or CLI. The way you have a STL format, we have SLC or CLI. SLC is related to slice. CLI is called common layer interface. So there are formats in which these polygons, nested polygons, are being written and these files are being used by the 3D printer in order to generate the laser scanning paths or the material deposition paths, correct? And basically we have these different kinds of systems. So liquid based systems are there, and you have powder based systems, you have solid based systems, correct? So I'm not going to explain much about these things. Then basically you have post processing, correct? So once you get the component, it may not be fully cured. This situation generally you get in case of stereolithography. In stereolithography, once it is the situation, you are going to put it in a oven, and you're going to have the things done. Post cure, and then removal of support structure. So removal of support structure you try to do because it is an inherent capability, or rather inherent characteristic of 3D printing, because if there's any overhanging features likely to come, you have to plan for the support structure, and the support structure is to be removed later on, and then because of the still stepping effect, you have to do some finishing by sanding, polishing, short cleaning, painting, or maybe sometimes in case of FDM or plastic component, you do acetone, this vapor treatment in order to improve the surface quality to very fine quality. So basically in a very short time, maybe in few hours time, you get a physical prototype from the virtual CAD model. So that's why it is called rapid prototyping. Now today we have different inputs. Obviously 3D CAD and 2D CAD, and you get STL and you can use a 3D printer, but there are two very interesting applications. One is reverse engineering. So in reverse engineering, we take the point cloud data, we scan point cloud data and use it. You make either using some software of reverse engineering, we try to develop 3D CAD, or we directly develop STL file to point cloud data, and we operate a 3D printer to get the component. And for biomedical application, which is very interesting in my view, because the full capabilities of 3D printing, because if you really want to make a implant or a model, bone model for a particular patient, it is quite specific, very customized for a particular patient. So that's why you are taking MRI or CT scan data as an input, using softwares like Mimics or Simpleware to reconstruct the things, get the STL file, and then you are actually using the data in order to do the things. So this I have already explained, that if you bring in RP as a product design tool, you can bring down the manufacturing lead time to a minimum that may be sometimes as small as 10%. So this is what various projects have reported. So if you really use this 3D printing technology in your industry for new product design and prototyping, you may be the someone, if you are among first few who are actually the players and who are launching a particular product in the market, they are the best profit makers. Correct? Later on, when the number of players comes, there's a lot of competition and you cannot produce that much of profit. So squeezing down the manufacturing lead time is something which is very important. And as far as the product development activity is concerned, it is a very, very important and point of breakthrough, which can actually bring laurels to your business. Okay, but definitely there are number of I'll say barriers. I'll talk about that if the time permits, which are not enabling us. The reason why really our Indian industry is not adapting this technology with open hearts. So anyway, so there is a classification, and yeah. So I'll call you. I'm in a lecture, so I'll call you. So this is something which is called classification of AM. So this, I believe you know that there are solid-based process, liquid-based, and you have stereolithography, FDM, and you have number of other processes too. So let me go back and I'll show you. This is stereolithography. So here basically from this technology only, the concept of rapid prototyping, or today we are calling it 3D printing, has started. In 1994, the first patent appeared for stereolithography, and Here, the idea was actually the material. A very specific material is being used, and that specific material is called photosensitive monomer or polymer, whatever you call. Because in the beginning it is monomer, and later on when it is exposed to a certain wavelength light, above that you will find it becomes polymer. It hardens. So the liquid resin which is being used is actually a photosensitive monomer, which is being acted by a laser beam. There's a photolytic reaction, and because of the h nu, that is the h nu has to be greater than some nu star, that is the frequency of the laser, and wherever this laser spot goes, you will find that there's a formation of voxel, and you are able to make the things harder. So you'll do one layer, then the platform will go down, you will another pour the liquid again, and you will again keep on adding the material. So this is how the things go ahead. Okay, now this is the selective laser sintering oblique melting. So instead of this is another development, very. So let me talk about the pros and cons. Now this is definitely a breakthrough as an invention, which because of which we are today talking about additive manufacturing. And this process is good because it has good resolution. Liquid can be deposited in a very thin slices, so the accuracy and the surface quality and the resolution of the process is high. But the limitation is that the very limited number of photosensitive materials are available. Then laser sintering is something, when we talk about it, is a powder bed kind of system. So here we deposit the we spread the powder through this recoater, and again there is a laser and there's a galvano mirror, and the laser spot moves, and wherever the laser spot goes, the fine powder, they get melted from its periphery, and they get entangled, or rather they form a lump basically. So it's very much unlike to the basic concept of powder metallurgy, where we try to study sintering. You should not get confused that there's any kind of application of pressure or compacting or then taking it to the furnace. No, it is a pressureless spreading of the powder, and when the laser spot comes, it gets melted at the periphery, and it gets connected to the neighboring particles. So that's how the solid lump is being formed. And in this case, you need not to deposit the support structure, because the support structure, the unsintered powder behaves like a support structure. So you can see from this figure also that you are spreading the powder by this recoater and the laser exposed laser beam. So this brown color thing, it is the sintered material, and yellow color is unsintered, which is acting as a support structure. The platform moves down, and then again you recoat. So this is how the process goes on. FDM, you all know what it is. So many things you might have already studied about FDM. LOM is something which is where the laser is used to cut the material. So here you are having basically the sheet material which is being stick to this platform by laminating roller, and you are actually having this laser which cuts the material. So actually this ring is something which is desired, and all other materials are unwanted material. So we are cutting it and taking it away. And then today we have advanced technology. So there has been another concept of powder blow systems. The powder bed system is like SLS system. So we call it SLM when we talk about say metal. So like here I can have polymer powder as well as metal powder. So if I am using polymer powder, I cannot go much. Like the temperature requirements are up to 300 maximum, and if I have to use metals, it will depend on the kind of metal we are using. So because in all SLM technologies, we are even going for super alloys deposition. So we go for up to 1400 degrees Celsius temperature, maybe more also sometimes. And you have to conduct this process in a proper environment. It may be inert environment or a proper environment, so that the material does not react with this thing. Okay, then another concept is flow, powder blowing system. So here the development started around 2006, and you have number of parallel developments. So one development took place at Sandia National Laboratories, US. Another was at Michigan University, and maybe some others. So here they called it LENS, laser engineered net shaping. And the Michigan people called it DMD, direct metal deposition. Nowadays, a new term has come, direct energy deposition. I do not know what is this direct energy deposition is. You cannot deposit energy. If I see the terminology English-wise, direct energy deposition. So I don't know how you can deposit energy, but maybe it is becoming very popular. Then there's another term which has come, laser metal deposition. So laser metal deposition, that is an L. I don't know the English, laser metal deposition. So it is actually metal deposition and melting by laser. So the system is almost similar. You can see, I'll show you some videos too. So the powder comes like this. It is blown, it is suspended, it is pushed through some gases, obviously inert gases, because it is a metal powder. And from the center you are having laser. When it interacts, fine droplets are formed, and there's XY control, and you are able to deposit structures like this. So this is called a powder bed system, a powder blown system. And you can see the interface. So in case of powder blown system, you have an interface like this. And in case of powder bed system, this is a metal powder, and the laser comes and scans. So you basically, this is the sintered material. So this is how the laser spot. You can see the interaction of material with the laser and the process zone. You can just have a look. So finally you get a component like this in this case. Okay, now before moving to the applications, let me talk about some advanced manufacturing AM processes. What happened? Yeah. So let me talk about these advanced manufacturing processes. So I'm also calling it direct energy deposition, because people call it, though I don't know what is direct energy deposition. So you can see that the concept is, again, that powder comes from here in an inert gas atmosphere. You are doing, there's a pyrometry, there's a laser, and basically here is a focal plane. It gets, this thing, and then you are able to actually melt it and deposit. So it's called DED. And so you can see the video. हाँ गौरव, मैं आपको फोन करता हूँ. हाँ नमस्कार नमस्कार, मैं एक क्लास में हूँ अभी, है ना, फिर फोन करता हूँ. और क्या चल रहा है वहाँ, ज्वाइनिंग वाइनिंग हो गई, क्या चल रहा है? मूड नहीं बन रही. एक्चुअली मुझसे देशमुख जी पूछ रहे थे, क्योंकि वो पता नहीं रविशंकर को कैसे पता चला, तो वो उन्होंने देशमुख जी को बताया होगा, तो वो मेरे से कल पूछ रहे थे. मैं पता करता हूँ. हाँ हाँ, फिर मैंने यहाँ का भी बताया, यहाँ पे बिहार में भाई लोग बुलाते ही नहीं. Okay, so there's another video which is self-explanatory. There may be a different kind of torch. It is on the on it is basically mounted on a robotic kind of system. Okay. So there are I believe you would have already appreciated the process. So here the pros, that is the advantages, are suitable for fabricating multi-gradient materials. So you can create, functionally graded materials that different from different passages. You can have different powders, different material powders with different flow rates, and you can continuously vary the material flow rate or material composition, and that's how you can have a functionally graded material. And then you can have a fast build and rapid material deposition. You can have very dense parts. Support structures not needed because you are having multi-axis systems and can be used even for repairing of the components. Now, if you want to do repairing of the component, you need to have the CAD model of the original component. You will produce the CAD model of the worn component, which needs repairing, and you will do the subtractive operation. So you'll get the geometry of the worn part, and so considering that as a CAD model, you can deposit the material using this kind of technology. So the limitations are that it has poor surface finish, significant post-processing is needed. One big thing is that you need wire cutidium, because from the platform itself you have to remove the complete component. So you need that. Part complexity is limited, but it has different application in different domains, correct? So obviously there are focused application, but you can see that in different domains you can have the applications. Okay, so then laser metal deposition is another variant. Similar concept. You can see only the design of nozzle, and here and there are certain changes, and there may be some changes which are not known to anybody because in the controls basically, but from the uh, outside, if you see, the concept looks like similar. And then basically here also the challenges are that you have a very complex thermal histories, process structure property relationship is still not established. Anisotropy is there in the mechanical structure because of the layers and because of the porosities, and it is an expensive system. Distortion is less, definitely. Then people have also used electron beam in place of laser beam. So definitely the two variants. You have a powder bed system. So everything is similar except that you are having a electron beam of high power, that is around 3 kilowatt, instead of laser, and you are doing everything similar, but able to make the components on powder bed. The advantage here is it's a vacuum process. Not advantage, it is a vacuum process. Of course, it becomes costlier then, and but because of this, it leads to elimination of impurities and excellent mechanical material properties, mechanical properties. The another version may be the wire based version, that instead of powder you are having a wire feeder and there's an electron beam, they interact and you are able to deposit the material on this. So you have different advantages and limitations, and you can see the various applications now, that uh, the different fields this particular process has applications. So then we have wire arc additive manufacturing, that welding. Of course, the MIG welding has been used to develop process. So you can see the process video. Uses an arc welding process to 3D printed metal parts, and process is controlled by a robotic arm. This is another video. Okay. Now there are a number of benefits of VAM. So it has a uh, large range of deposition, and near net shape and therefore reduced material loss, fast process, good structural integrity, but the surface quality and residual stresses are high. And for very reactive materials, if you want to do, you need shielding gases, and it is a low resolution. You can see the walls which have been produced, so you can appreciate the kind of finishing and the kind of distortions which are being achieved. Okay, now this is the application of VAM, different components which people have produced. So I have marked the source also. So I don't get money to do all this thing, correct? I'm a very economical professor. Then multijet fusion printing technology. This is another technology which is introduced by HP. You all know HP, correct? It is also not so old, maybe 3-4 years old only, maybe more. But I have introduced in Noida. There's a company 3 to 4 years back only. So here basically you are spreading the powder like powder bed, and you are using two kinds of chemicals. One is called a detailing agent and one is called fusing agent, to make the the component where you really want it to be hardened and become sintered, and then you are at once exposing the UV light. So in one go it goes. That's why you are able to make dense components, and you can see there are different patented materials they have. So one patented material, you can create very flexible components, that is for polyurethane, and you can make strong components from polyamide. So basically it is a high resolution and very high dimensional accuracy process. That is the benefit, and these are the various components which have been produced by this process that you can see. So this is all acknowledgement from various sources. I have taken the material. Then another process which I have come across, talking about FDP like you only, then I could come to know. So I read about it and made the things. So this is digital light processing. Very much similar to stereolithography, but instead of
project the image of an entire layer simultaneously, regardless of the number of parts.
So here, instead of laser, we are using light.
Flash, PLP printers can be outstandingly fast.
So what is
They're
being
also
done?
very reliable with low complexity and minimal.
So what happens here that in case of stereolithography, you are using laser spot to move, but here at once you are exposing the things like this, and the entire layer is exposed in one go. And basically you are having some digital system which I'll show you. It's like LCD. So certain part becomes opaque and certain part is it's transparent, so the light passes through it, and you are projecting this kind of film on this, UV light on this, and the resin that cures. So that is called DLP. So this is the picture. You can see that there's a minimum spot size of 30 microns you're getting. Smaller the size you'll get, costlier will be the printer. So in SLA you get basically point, but here you are exposing the entire layer, and that's why what happens is the DLP process becomes faster if the component has larger sections. But if the component has small sections and there are very intricate details, it is the stereolithography that may give you the better results. So these are the different geometrical situations. You will find that which process is better in which case. So these are the different components which have been produced by DLP. Every company shows and does their advertisement. And then we have 2-photon polymerization process. So 2-photon polymerization process is another important process where we are actually again using polymer, and it is the photopolymer. And instead of having laser beam that is parallel laser, we are used conical laser here, and that's why the energy gets concentrated the way it has been shown here. So voxel here actually the polymerization takes place and you are able to deposit a voxel, and that's why the size is very small. You can control the size by this laser intensity, or by varying the laser intensity, or maybe by cone angle, or by focusing in a different way. So in this process, the small volume that is being deposited, so the resolution is very high, that is approximately 100 nanometer, and it is complementary to 2-photon microscopy process. Online process observation is of course there, and the advantage here is that the size, this 100 nanometer, is much smaller than the biological tissues and cells. So that's why you can do the polymerization, or you can do the 3D printing even in the presence of biological tissues. So it is very important process for tissue engineering applications, and that too for micro level. But you need biocompatible initiators, you need monomers with low toxicity. So there are various fields where you are actually having this thing done, that is application of 2-photon polymerization. So you can see that in the field of metamaterials, tissue engineering, photonics, MEMS, in different fields, this particular process has its applications. And then, so this is another important slide which gives you a feel of the potential of this process. So it is for micro optics. These are the prisms. You can see the dimension. 60 micron is this dimension. It is a lens. It is a micro lens having this. Its diameter is around. Its radius is around, I'll say, 50 microns. This diameter is 100 microns only. This is a scaffold. Tissue engineering scaffold. This dimension. This width may be around 200 or 150 microns. You can see the kind of accuracy you can have. These are the micro needles. So these micro needles are used for drug delivery, painless drug delivery applications. So they can be produced. They have been produced by this particular process. So this is all about. Then I'll talk about Markforged 3D printer, which is for deposition of I must say composite material. So this printer is actually based on the concept of FDM, that is fused filament fabrication. So if you see this fused filament fabrication, you will actually enjoy this Markforged 3D printer. So let us see this printer also. Okay, so here basically there are two ways you can do. You can have alternate carbon fiber spool and nylon spool, and using the concept of FDM, these are the two spools. Very fine, this wires are there. It's unlike FDM, where we have around I'll say 1 mm diameter or maybe little lesser diameter wire, and we are able to deposit it the way it has been shown here alternatively, and we get. Then we also have material they supply called onyx. So here chopped carbon fiber, this thing is there. So it is an onyx material, and you have carbon fiber, then you have glass fiber, Kevlar fiber. So you are able to actually deposit the material alternatively, or maybe sometimes with chopped material, chopped fiber material, and you are able to deposit variety of uh, uh, composites, correct? But the principle is basically fused filament fabrication. So you can make different components which are actually which can be used for real-time application. You can see there's a shock absorber which has been developed by onyx material. Then we have, this is a carburetor which has been developed by this composite material, and this is a jaw for holding this workpiece during machining. So they have all been done using this kind of composite material. So very interesting. We have this printer with us. I could not do any research work till now with these things. So I think I have taken a lot of time. Now, so I believe that this may interest you. Now let me go to some interesting biomedical research applications which we have done at IIT Delhi. So this is one slide which I have developed for this Vaibhav Summit, and it was delivered some time back on October 14th. So this is a very interesting research work which we have done at IIT Delhi, and the boy is from Punjab only. So let's give him big hands to the boy, because it is a very interesting work he has done. And we have actually developed this 3D printer in our lab. This is a solvent cast 3D printer, and here we are developing bio ink, which is based on certain bio resorbable polymer and with some solvent, and we are depositing the material on rotating rod. So this is the innovation part which we have done. So here on rotating rod we are depositing, and we are able to make this cardiovascular biodegradable polymeric cardiovascular stents. They are implants, basically cardio implants. So different designs, like you have to make the CAD model, feed it to it, it will make. So different designs can be made. And then we have, like when you do angioplasty, you do ballooning. So we have done the testing for ballooning. So we did the radial compression bending test as per the standards for these particular stents, and we did the ballooning test also, and we did the biological testing also. So this is the results of biological testing, and we did the degradation test. So we mimicked the heart function. So this is a pump which we got, and on this silicon rubber we are having the stents placed here, and you can see these are the stents which are here. I have shown schematically, and this is pumping like heart. So we are like, what happens, these metallic stents, they are always present, but they will degrade after few years. So that's the idea. So we were in touch with some doctors also in AIIMS. So this concept was developed, and this boy has defended his thesis with very nice comments, and this is wonderful work. We had copyright of various algorithms we have developed. We have 2 patents on this particular thing which we have developed at IIT Delhi. Then we have developed another concept of 3D printing, where acoustic liquid manipulation assisted jet electrochemical micro deposition we have done. So it is actually the high-speed jet of electrolyte, and it can deposit like this. But if you, so this is called edge effect. So if you superimpose ultrasonic vibrations, then you are able to get very fine, smooth features. So with ordinary DC supply, you get very large grain size, but once we used nano pulse DC, we get nano particles in the structure. So now we can proudly say that I can deposit a micro component I can deposit, and I can ensure that every grain present in that micro component is a nano grain. So this is an entirely different kind of work which we have done at IIT Delhi. This is another very recent, and so every work has patent. Now this is another very recent works, 1 or 2 years old. We have developed biodegradable pure iron implant, and because now again the trend is biodegradation. So if you are using iron as pure iron as an implant material, it has stress shielding problem, and at the same time its degradation rate is very low. So we have tried to improve its degradation rate and reduce the problem of stress shielding. So we have developed our own system. So you can see the kind of accuracy we have got in our microwave sintering along with this stereolithography. Even you cannot make it with metal deposition systems which are recently, the kind of accuracy, the kind of surface quality which we have achieved, you cannot get from the commercial systems which are available today. This is another important work done by a GNU student, Gurminder Singh, correct? So here we developed another ultrasonic assisted pressureless sintering process for rapid manufacturing of, these are the structures which we developed. Once again, copper deposition is quite difficult even with SLM and maybe some powder blown processes, and the accuracy and repeatability is very bad. So these structures we have developed, and with a new process is new, the application is new, and the geometry, the complexity of the geometry you can imagine. Then again, wonderful piece of research work where we developed this clubfoot, Orthosis. So these are the silicon rubber clubfoots of the babies which we could contact at Delhi and Chandigarh region, and we could basically develop there. So this work is a little older work, completed in I think 2013 or 14. And this is the kind of orthosis we developed, and we did clinical trials also at SGPGI Chandigarh. So this is all being done, and this is a measuring device for clubfoot. This is what we have developed at our place. So now let me go back to the this particular piece of this thing that for which you have written the topic. Yeah. So let me explain to this the concept of ultrasonic bone drilling. Of course, I'll not say that there's a direct involvement of 3D printing work here, but the entire knowledge which we keep acquiring in this particular work in this field, that has actually helped us. So we have developed a bone drill prototype. So this is all general introduction. So basically, when you try to drill a hole, you get heat generation and there are cutting forces. So problem is of that hole inaccuracy is there, micro cracks are there, and bone may break, and there's a thermal necrosis. Because of the temperature rise, you basically get the tissues, they burn. So this whole problem called osteosynthesis. So we have developed our own process where we have developed rotary ultrasonic bone drilling system. We have patent of this machine also. So here is an ultrasonic vibration and there's a tool. So actually, frankly speaking, tool is something which is very novel. So how this tool is, so first just have a look on this. So this is the whole geometry on the, this is bovine bone results. And if you do with conventional surgical bone drilling, which is the which doctors are using nowadays in operation theaters, this is how the hole looks like, and you can see this is all burning of the tissues. But once we do it with our process, you can see the geometry and there's no burning at all, and you can see that there are no micro cracks if you are doing it with lower feed rate and proper process parameter. Let me summarize that way. But in case of RUBD, so no evidence of having any cracks, or if at very high process parameters there may be cracks, but they are very little. This is called histopathological study which we did at AIIMS. So once we do it with RUBD, you will find that the drilling site is very smooth, and all these red dots which you are observing here, they give you evidence of the live cells even after 3 months of the hole being drilled. Okay, then later on, with this concept, we have developed a prototype machine for this purpose. So we kept on doing so many things. These are the intermediate steps. But finally, a machine like this has been developed. It is available in our lab. The final work slides I don't have right now. So this is how the tool was developed, and this is the tool actually. So this is actually the major innovation in our part, that we could develop this design of the tool which actually vibrates. So here it's not the geometry, it is actually a horn. It is actually a horn of the ultrasonic system. So you have to do the tuning very properly. So the dimensions, the materials, and having this coating of diamond abrasives by electroplating, this all has to be, it is actually a design problem, frankly speaking, correct? So there's an innovation involved and you have to design it mathematically. So this is our final tool, and this is all developmental stage slides. So this is how we have taken the ethical clearance from IIT Delhi and AIIMS, and finally we could develop this machine. The prototype is available and it is ready for we are looking for certain companies who can do the commercialization of the system. And this particular work was sponsored by Srishti Bairak. So I do acknowledge to their funding which we have received from there on the name of Dr. Vishal Gupta, who worked in the beginning, and later on Ravinder Singh has taken this work up to this side. So thank you very much for your patient hearing of my this long talk. Anyway, so I think I tried my best to deliver you what I can do. So now this session, I think I'll hand over to Dr. Rupinder Singh, and maybe some questions, etc. Whatever we want to conclude it here.
Sure. Thanks, Professor Pandey, for the elaborative discussion. We have a lot of such components to move forward within this area. Dear participants, now the panel is open for discussion. If you want, we can have one or two quick questions from Professor Pandey.
Yeah, any question? There's a question SLM and DMLS. Actually, this we can discuss this part. You know, there may be, it is a matter of only process parameters. Correct. There may be a situation that you are melting little more, or you're melting only on the peripheries. So more or less, there is a similarity. Yeah.
Sir, okay, there is another question. Can we drill the parts of jaw or insert a printed teeth?
Could we drill the parts of the jaw to insert a printed teeth? You, like I have shown you one printer called Mark Forged, which can even be used to make shock absorbers. So if you use that printer, you can definitely make a jaw. And yeah, so the concept of 4D printing, I believe, like I give a very nice example. Like in 4D printing, the concept is emerging, correct? So in 4D printing, there's a fourth dimension. This dimension is not related to geometry, correct? But it is related to change in the 3D printed component geometry by application of certain external energy, or we call them as stimulating fields. So the stimulating fields may be heat, it may be temperature, it may be magnetic field, it may be gravitational effect, it may be some other kind of effect, correct? So like if I give you a very simple example, suppose you print a rose flower, you print a flower, and flower is like this, correct? And you are putting some sort of magnetic material along with that polymer, for example, or it is made of only, say, some sort of ferromagnetic material, very thin. It is like this. Foils are there, and then you are having some electromagnetic space. When you are switching on the electromagnetic, because of the electromagnetic effect, you get that flower opens. So this kind of structure, if you're developing, it is called a 4D printing concept. So when you are actually producing, it is a 3D only. It is 3D printing, but it gives you a actuation, correct? When it is being stimulated or it is being energized by certain external energy. So if you are designing such a system, such a component, the application is known as 4D printing. So you can think of some interesting application of 4D printing, and which can be used for any industrial application. So I think we are doing some work in this direction, and maybe in a year or so, I may be in a position to produce some interesting results in my forthcoming talks. So with this, I think I must close here, because I have already delayed. Generally, I do not delay my lecture. I apologize for the same, because another speaker will be waiting. So thanks a lot for patient hearing. And if there are any more questions, you can visit my website. My mobile number, my mail ID is there, and you can always approach me. There's no problem. So, Professor Rupinder Singh ji, I think I must close now.
Sir, thank you very much. Sir, just last concluding question, what I want to ask, do we think of some 5D or 6D printing also?
Actually, these things are very, like, you can, there are, if you type on, Google, there is a company in Bangalore, they are claiming that they have done 5D printing. But actually that is not a 5D printing, that is a 5-axis printing. Correct? 5D is a different thing at all. It is a 5-axis printing. You have X, Y, Z, and they have a rotary table that has a rotation like this and that has a rotation like this. Correct? So there's a rotation this way, there's a rotation this way. So you have X, Y, Z, and A and B. There are two rotations, or you can say B and C, based on the standard notification or the standard way of designating the axis in case of CNC. So that is a 5-axis printer. It's not a 5D printer. Correct? So what concept you are having in your mind, that 5D printing or 6D printing, that is a different issue altogether. Like here, fourth dimension is actuation. So if you can bring something else also, correct? You may say that there is some biological evolution also along with fourth dimension. So then that may be a fifth dimension. But just rotating the table and printing on something different, you cannot call it as a 4D printer. Like the printer which we have developed, it has a rotary axis. So I can also say that X, Y, I can take it up and down and it is rotating. So it is a 4D printing. No, I never call that my system is a 4D printing system. Is it okay? It's not fourth dimension. It is a 4-axis. It is not 4D. So there's a difference in the terminology. So anyway, I think I must stop here. Okay.
Thank you, Professor. Thank you for your elaborative discussion. We learned a lot of things from the research point of view, and you are really a person with light showing for work in the area of 3D printing. Thank you, Professor. Thank you very much.
Thanks a lot, and looking forward to meet you sometime in Delhi. Let the period come to an end. So thanks, Rupinder Singh ji. Namaskar. All the best to everybody. Good day.
Thank you, Professor. Thank you very much. So, dear participants, we take a small break and we will reassemble at 12 noon. Thank you very much.